Hello, in this video we'll deal with the Nobel Prize in Chemistry from the year 1906, awarded to Henri Moissan. And why did he receive it? For his investigations and isolation of the element fluoride and for the electric furnace called after him. Some more detailed information about why he received the prize. Investigations of various salts and minerals during the 19th century led chemists to suspect that there was a previously unknown element with properties that resembled chlorine and iodine. However, it was very difficult to isolate the substance. By developing an ingenious apparatus, Henri Moissan succeeded in producing a stream of gas consisting of the sought-after element fluoride. In 1886, Moissan also developed a new type of furnace in which an electric arc is used as a source of heat. In the furnace, Moissan managed to synthesize microscopic diamonds and other materials. This, of course, as always, coming from the official Nobel Prize site. Here you see the link to it, which will also be a link in the description under the video. Here you see the man at work making his diamonds with his furnace. Okay, some background information also coming from the official Nobel Prize site. Henri Moissan was born in Paris in September 28, 1852. His advanced education began in the Collège du Mans and later in Edmond Freeney's laboratory at the Musée d'Histoire Naturelle, where he attended lectures by E.H. Saint-Clair de Ville and Henri Debray. A year later, he moved to Derain's laboratory in the École pratique des hautes études, and subsequently he directed a small laboratory of his own before joining Debray and Trost in the laboratories of the Sorbonne. He was appointed to a junior position in the Agronomic Institute in 1879, and he gained his doctorate in 1880 with a thesis on the cyanogen series. He became assistant lecturer and senior demonstrator at the School of Pharmacy, and in 1886 he was elected professor of toxicology. In 1899 he took the chair of inorganic chemistry, and in 1900 he was appointed assessor to the director of that school. In the same year he succeeded Trost as professor of inorganic chemistry at the University of Paris. Moissan's first researches concerned the interchange of oxygen and carbon dioxide in the leaves of plants. He was soon to leave biology for the field of inorganic chemistry, where his early work was on the oxides of the iron group metals and chromium, and the study of the chromous salts. In 1884 he turned his attention to fluorine chemistry, preparing some organic and phosphorus derivatives of that element. The following year he discovered that solutions of potassium fluoride in hydrogen fluoride at certain strength remained liquid and conducted electrochemically at sub-zero temperatures. A year later he successfully electrolyzed these solutions to isolate fluorine for the first time. He made a full study of the properties of the gas and its reactions with other elements. In 1892, Moissan theorized that diamonds could be synthesized by crystallizing carbon under pressure from molten iron. He designed and developed the electric arc furnace, attaining temperatures up to 3,500 degrees Celsius to a system in work, which led to the production of tiny artificial stones. He subsequently used the furnace to volatile many substances which had been regarded as infusible and to prepare many new compounds, particularly carbides, silicides and borides. In 1891 he discovered carborundum. His close study of the carbides and their reaction with water led to his theory that in some cases petroleum may be formed by subterraneous reaction between carbides and water. He prepared the hydrides of calcium, sodium and potassium and showed them to be non-conductive, and using the electric furnace isolated many metals. Moissan is credited with over 300 publications, his greatest work being Le Four électrique, the electric furnace, Le Fluor et le composé, fluorine and its compounds, and Traite de chimie minérale, treatise on inorganic chemistry, 5 volumes. He was an excellent lecturer and a meticulous and patient experimentalist. He suddenly died in Paris on February 20, 1907, shortly after his return from the prize-giving ceremony in Stockholm. So he could not enjoy his Nobel Prize for very long, unfortunately. This information, as always, from the official Nobel site, a link to it in the option under the video. Here you see some pictures from one of his books on the fluoration of fluorine. Here again, beautiful drawings. Then the award ceremony speech given by Professor P. Clausen. When Lavoisier presented his antiphlogistic system, the system proved in principle so perfect that one could confidently predict that many well-known substances such as alkalis and alkaline earths were not elements but oxides of hitherto unknown metals, a theory which Davy, by means of electrolysis, soon after proved to be correct. However, Lavoisier's system was not perfect in every respect. The very prototype of all salts, common salts, had no place in it. When once the negative principle chlorine, which is one of its constituents, was thoroughly understood, and more important, when iodine, a substance analogous to chlorine, had been discovered, it became clear that in substances a new class of elements, the halogens, had been found. This led to the conclusion that hydrofluoric acid, which has been discovered by Scheele and studied more fully by Berzelius, must be assumed to contain a negative element. Fluorine, which was completely analogous to other halogens, which in participation was given its place besides oxygen at the head of the halogens. But all effort to isolate it failed until 1886. Then Moissan found the way to an ultimate solution of the problem. The difficulty lay partly in the enormous energy possessed by this element, thanks to which it would decompose water in the cold, and partly in the fact that hydrofluoric acid, which seems to be the substance most capable of yielding fluorine upon hydrolysis, was a non-conductor of electricity. However, by means of a series of ingenious arrangements, Moissan succeeded in overcoming all these difficulties to such a degree that this element could now be obtained in a continuous flow of gas for hours on end. This result enabled Moissan to carry out a very thorough methodical study of it. So far, the most important outcome of this research is that fluorine has now been proved to possess all the qualities previously attributed to it by virtue of its position in the system as a reinforced oxygen. Thus, at ordinary temperatures, it combines with carbon and silicon, forming gases. It combines with hydrogen at temperatures as low as approximately minus 230 degrees Celsius. When hydrogen unites with this element, also more heat is released than when hydrogen unites with oxygen. Some of its compounds, for instance those with sulfur, are of great importance for determination of the valence of the elements. Moissan's ultimate goal in his work on fluorine was to complete a brilliant series of mineral syntheses, which had brought great renown to several of his compatriots by producing artificially the most remarkable and at the same time most precious mineral, the diamond. This meant employing a hitherto little practiced method. The possibility of using an electric arc as a means of heating was already evident. Moissan had a very simple but brilliant idea of using it to produce heat while at the same time excluding all side effects. In a celebrated electrical furnace, he succeeded in liquefying substances such as lime and magnesium oxide. In this way, he produced calcium carbide and a whole series of other carbides in pure and crystallized form, from which it was found that carbides were the most heat resistant of all chemical compounds. It was now possible by decomposition of the carbides to produce in pure ingots metals such as tungsten, molybdenum, and titanium, which had hitherto been obtainable only in powder form. Again, with his furnace, he produced microscopic diamonds by suddenly cooling at very high temperature a molten peak of iron containing carbon. This experiment is very instructive. The carbon gave transparent drops, shared diamonds, which were in every way similar to the microscopic specimens found, for instance, in the diamond-bearing strata at the Cape. And this apparently explains how diamonds are formed in nature. Moissan also made a methodological study of graphite, and he showed, effect of great interest, that graphite becomes what it is known as swelling when it is extracted from a metal solution prepared in an electric furnace. Since a number of native irons, among them the iron found by Nordenskjöld at Ovivak at Greenland, as well as the diamond-bearing strata of the Cape, contain graphite in the swelling form. The work done by Moissan with the electric furnace gave to the world of technology an impetus which will be felt for a long time, and it's still impossible to measure the extent and significance of the effects which this invention will have. This, of course, again, coming from the official Nobel Prize site, the ceremony speech. Here you see some of the pretty beautiful drawings from one of his books. It is probably the famous furnace he was working with. And again. Okay, this was it for the moment. Next week we will continue with this Nobel Prize, and then we turn to the Nobel Prize lecture given by Henri Moissan. For now, thank you for watching, and maybe till another time.